Hello, good people, and welcome back. Well, so in this video, we're going to continue from where we left off, and we ended up our discussion in the last video talking about this bootstrap method that we use to reconstruct a zero curve. Um, Now we can apply the same methods to the OIS rate, and you remember that the OIS rate are the risk-free rates that are going to be used, that we're going to be using essentially for the valuation of all those derivative instruments that we've been studying all along, including the swap agreement, right? And actually, the OIS rate for maturity that are greater than 1 year are considered to be equal to the swap rates, and those are what we refer to as par yield here. We'll see how this works and how this functions well when we actually work on valuing swaps a little later. For now, the things that I want you to remember or to get from here are the fact that OIS rates for maturities that are less than 1 year are essentially equal to the zero rate. So if we have an OIS rate for a maturity less than 1 year, that's going to be equal to the 1 year OIS rate is going to be equal to the zero rate that we just computed here. The 6 months OIS rate is going to be equal to the 10.496% here, and the 3 months OIS rate is going to be equal to 10.127%. Again, what does that mean? Here is the OIS rate is equal to the zero rate whenever we have a maturity that's less than 1 year. Now, if the maturity is greater than 1 year, then we need to compute the par yield, and the par yield is going to be equal to our OIS rate, and that is in a way to address concerns with respect to arbitrage. And you remember that the par yield is that coupon rate that would make the present value of all the cash flows that equal to par value. In this case, we found in our computation earlier that the par yield was equal to 100 minus 100 multiplied by D multiplied by M divided by capital A. And we said that this capital A was essentially the sum of the present value factors. The M is the number of compounding period, and D here was the last essentially present value factor. And that is how we computed our par yield essentially. And what we're saying here is that beyond the 1 year, the OIS rate is equal to the par yield. This is also our fixed rate for swap agreement. And we'll talk some more about this a little later. Next, what we can do is compute forward rate. And what forward rates are essentially, they are spot rates at some point in the future. They're expected future spot rates at some point in the future. So a forward rate is a future zero rate, and the zero rate, another name for the zero rate here is also spot rate, implied by today's term structure of interest rate or today's zero curve. So the term structure of interest rate that we're talking about really here is our zero curve. So let's look at an example here on our board. Let's say we have $100 to invest, and we wanted to invest $100 for 3 years. So we could do that for 3 years. 1 year, 2 years, and 3 years. And so if we did that, what would be the future value of our investment if the interest rate were to be, or the zero rate for 3 years were to be, let's say, 4%. Well, if the interest rate, actually let's just read from this table. If the interest rate for 3 years is 4.6%, at 4.6% for 3 years, that's our zero rate. for 3 years, we would be doing 100 multiplied by exponential of the 4.6% multiplied by 3. That's how we would get our future value. Now, we could do that. That's one option. Another option would be to invest that $100 for just 2 years, and then once we're done with the 2 years, so 1 year, 2 year, once we're done with the 2 year, we get whatever amount of money we have there, and then we reinvest that for another 1 year so that we actually meet the 3 years. And the question is, well, what is this? The 2 years rate that we would use here would essentially be the 4%, which is the 0 rate for 2 years. So that's going to be a 4%. And the question here would be, what is this last rate here that would make this future value exactly equal to that amount? Well, that last rate would essentially be computed as follows. So we would have $100 multiplied by the exponential of 4% for 2 years. And that will give us whatever amount we have here. And then we grow that amount again by the exponential of, let's call that RF, for 1 year. And we want that to be equal to the following. So I'm just going to change the color here. The exponential of RF for 1 year. Let's call this RF. And that's for 1 year. And we want that to be exactly equal to the $100 that we have multiplied by the exponential of the 4.6% for 3 years. Now, we could simplify this by canceling the 100 that we have here, right? Because this is multiplication. And what we are left with is the exponential of 4% for 2 years multiplied by the exponential of RF for 1 year. That's equal to the exponential of the 4.6% for 3 years. And so if we remember our law of exponential, we can simply add the exponents there. So that would give us the exponential of 4. It would give us the 4.4% times 2 plus RF times 1. That's going to be equal to 4.6% times 3. So RF should have capital F here. RF, which is that rate that we are after here, will be equal to the 4.6% times 3 minus the 4.2%, the 4% times 2 divided by 1. And so that's what we have. Now, let's give this a slightly different name. Let's call 4.6%, let's call that R2. And so we're going to call T 3. So 4.6% with R2, we're going to call this T2. And the 4%, which is 2 years, we're going to call this R1, and therefore 2 is going to be T1. So what we find here is that RF, which is our forward rate, that's the answer here, our forward rate, is going to be equal to this value, 4.6%, which is R2. So it's going to be equal to R2 multiplied by T2, right? T2 is 3, so multiplied by T2 minus 4% here is going to be R1, so it's going to be R1 multiplied by T1, so it's going to be T1, and we're going to divide that by 1, but 1 is going to be the difference between, it's also 3 minus 2, and 3 is T2, 2 is T1. So it's the difference between the two. So that's T2 minus T1. And that's going to be our RF. So the forward rate is essentially computed as follows. And that's our formula for the forward rate. And what we're essentially saying is, for no arbitrage to exist, the future value of this investment of 100 for 3 years at the 3 years zero should be equal to a combination of the future value of the 100 for 2 years at the 2 years zero and the future value of that outcome for 1 year at the forward rate. So the forward rate is the 1 year zero rate 2 years from now. So the forward rate is the 1 year zero rate 2 years from today. That's essentially what we have there. So if we go back to our slides, we look at the formula to compute the forward rate, and that formula is essentially going to be RF for our forward rate is going to be equal to TR2, which is the farthest zero rate that we have there, multiplied by T2, that's its matching period, minus R1, which is the closest zero rate, multiplied by T1 divided by T2 minus T1. And that's essentially what we derived here. R2, T2, R1, T1, T2 minus T1. That gives us our forward rate. And if we go back here, all we did is that we assume zero rate for the period T2 and T1 are R1 and R2. That's essentially what we said. We said in this case that the zero rate would be R2 and R1 for the period of T1 and T2. Now let's apply this for a second. If we did that, what would we have? Our answer here would be, let me pull my financial calculator here and see if I can get it done. It would essentially be 4%. So that's going to be 0.046 times 3 equal, that gives me that, and 4% times 2, that's 8%, minus 0.08, and that gives me 5.8%. And the 5.8% is essentially this 5.8% forward rate there. So that's where that value comes from. So that value 5.8% comes exactly from this expression, where the R2 is the corresponding forward rate, zero rate for 3 years. The R1 is a zero rate for 2 years. T2 is 3 years. T1 is 2 years. And the difference is T2 minus T1, which is 1 year. So the 5.8% shows up here at 5.8%, and it is the 1 year zero rate 2 years from today. So 2 years from today we are here. It's going to be the 1 year zero rate 2 years from today. Alright, then that's our forward rate. This formula is only approximately true when we are using continuously compounded rate. That's correct, because here we are using continuously compounded rate, right? Whenever we use the e to the power of, we are assuming continuously compounded rate. And if that is true, then we can use this formula in order to find our forward rate. Now, if we can forecast or if we can estimate what the forward rate is going to be, or what the zero rate at some point in the future is going to be, it essentially means that we may be able to lock in that value at some point today, right? We may be able to lock in that forward rate today if we're able to forecast it. Because what this formula allows us to do is do just that. This formula allows us to forecast what the 1 year zero rate is going to be at some point in the future. Now, before we get there, we need to talk about the shape of the yield curve, right? And so far what we've seen is that the forward rate is going to follow essentially the pattern of the zero rate. So if we go back to our table that we had here, we'll see how our zero rate is upward sloping. That is, it is increasing over time. So our zero rate here is increasing over time. What it also means is that our forward rate there we go. Our forward rate is also going to be increasing over time. So they're both going to be forward sloping. Now, the forward rate is going to tend to be higher than the spot rate, right? Or the zero rate. So forward rate tend to be higher than the zero rate systematically. And it also turns out that the zero rate tend to be higher than the par yield. So the zero rate here are going to be higher than the par yield, and you remember how we found the par yield. And if I want to write that formula again for the par yield, that would be 100 minus 100 d m and then a. And we remember what a here is, the sum of all the present value factors. D is the last present value factor, and m is the number of compounding period. That's going to be our par yield. And so the relationship therefore is going to be something like that when the yield curve is upward sloping. So when the yield curve is upward sloping, what we're going to have is a forward rate that has the highest value. The zero rate is going to be the middle between the forward rate and the par yield. If our yield curve is downward sloping, on the other hand, our par yield is going to be higher than the zero rate, and our forward rate is going to be slower. It's going to be lower, and this is what an upward sloping curve is essentially going to look like. So in an upward sloping curve, we're going to have our zero curve here, our zero rate, which is going to be the middle one. And so our par yield is going to follow the pattern of our zero curve. So our par yield is going to be something like that, but it's going to be lower. This will be a par yield. And our forward rate is going to be a little higher, and our forward rate is going to be something like that. So this can be our forward rate. Alright, sorry about that. And we have here our zero curve. Alright, when the yield curve is downward sloping, what we're going to have is something like this, where it is downward sloping. So we're going to have something like that. So that's going to be our zero rate. And remember, our zero rate is always going to be in the middle, and so our zero rate is going to be that. So our par yield is going to be a little above that, so our par yield is going to be higher, and our forward rate is going to be lower, and that will be our forward rate essentially. Now, if we wanted to lock in, if we're able to forecast what the forward rate is going to be, if we're able to estimate the forward rate, we may be able to enter into an agreement or a forward agreement in order to lock in what that rate is going to be in the future. And those agreements are essentially what we refer to as the forward rate agreement, or FRAs. And those forward rate agreements are essentially over-the-counter agreement that a certain LIBOR rate or a certain rate would apply to a certain principal during a certain period of time in the future. Now this is really well understood with an example, and so we're going to work with an example in order to understand what the forward rate is going to be. But before we get there, let's look at the implication, then we're going to look at the example. So what are the key results for a forward rate agreement? A forward rate agreement is an equivalent to an agreement where the interest rate at the predetermined rate, that is RK, which is that interest we are locking in, is exchanged for interest at the LIBOR rate. So we are essentially exchanging this fixed rate for a LIBOR rate that we don't know what it is going to be at some point in the future. And so the forward rate agreement can be valued by assuming that the forward LIBOR interest rate, which is what we can forecast, that forward LIBOR interest rate is certain to be realized. So if we assume that that forward rate is certain to be realized based on our modeling or our assessment, we can enter lock in or value what this forward rate agreement is going to be, and you can tell what that value is going to be, right? That value is going to compare what we are locking in to what is likely to be. So what that means is that the value of the forward rate agreement is going to be the present value of the difference between the interest rate that would be paid, right, at the rate of the forward rate, the LIBOR forward rate, and the interest rate that would be paid at the rate RK, which is what we've locked in. So essentially what we're doing is the difference between those two rates, and we're computing the present value of that difference. So we could frame it as RK, which is, and that's not perfect answer there, so it's RK minus RF, and then we do the present value of that for a period of time. Now we're going to make an adjustment to this in a little bit and see exactly what that relationship here in a second. But before we get to this valuation, let's look at an example, and the example is what we have that follows. Our example says that a company has agreed that it will receive 4%, and so 4% in this case here would be the rate that we are locking in. So we're going to do that, label that RK, and we're going to be receiving 4% on the principal amount of 100 million. Let's label that L for that principal amount, and we're going to be receiving that for 3 months starting in 3 years. So let's go back to the board, and this is what we have. There is an agreement that's entered into, and this is today. 1 year, 2 year, 3 year, 4 years. So it's going to be 1, 2, 3, and 4. What we have is we are locking in today a 1 year rate starting 3 years from today. That 1 year rate that we're locking in starting 3 years from today is that rate that's here. That's what we're locking in, and that's what RK is, and that's what we're locking in at 4%. That's what our FRA stipulates, right? Our FRA says we're going to be receiving 4%, that 4% rate, but we're going to be receiving for a period of just 3 months. So this is going to be just 3 months within this year. So we're going to be receiving for 3 months in that last year on a notional, on a principal of 100 million. So our principal is 100 million. So what do we have? It means that we are expecting to receive 4% for a year, but then because this is just 3 months, so 3 months is a quarter of a year, so we're going to do a quarter of a year here. So we're going to divide this by 4 to make it the quarterly rate, and we're going to multiply that by 100 million. That is going to give us an expected 1%. So we're expecting to receive 1% multiplied by 100 million, and that is essentially equal to 1 million. That is what we're expecting. This rate here is based on our agreement. Now, this rate is always an annual rate, but because we are only receiving that for 3 months during the year, we need to adjust the rate to reflect that 3 months period within that last year, and then we weigh that by our notional amount or principal, and that's how we get that 1 million that we're supposed to receive. And so the next step that we're going to do is essentially to do the following. Go back to our slide and look at what the market expectation is. Well, we also say that the forward rate for the period between 3 and 3.25 years is 3%. So at this point here today, if we compute our forward rate just the way we did here in our analysis so far, if we compute our forward rate the same way that we've computed the forward rate for this example here, we would find that that forward rate is at 3%. So the forward rate, which is the 1 year rate starting 3 years from today, according to our calculation, is supposed to be 3%. And so if that forward rate is supposed to be 3%, how much money would we receive based on our agreement how much money would we receive if we had no agreement? If we had no agreement in place, we would be receiving 3% for the year, and because it's a quarter, we're going to adjust that as well. So no agreement simply means that we would be receiving the 3% divided by 4 multiplied by 100 million. And the same process rate, right? Because we are adjusting this for the quarterly period. Remember, if the forward rate is the 1 year rate starting 3 years from today, and because we are only receiving the payment for 3 months within that year, we need to adjust that, and there are 4 3-month periods within the year, right? 4 quarters. So we need to adjust that 1 year rate to the quarterly rate and then multiply that by a value. And so I'm going to pull my calculator here. So it's going to be 3 divided by 4. That's going to be equal to 0.75. And we're going to make that percentage. And we multiply by 100 million. 100, 1, 2, 3, 1, 2, 3. Boom, 750,000. So our value here is going to be equal to 750,000. Okay, so had we not entered in the FRA, we would have received 750,000. However, we entered into the FRA, which means that we're locked into that agreement. We will be receiving 1 million. So how much money do we earn from this transaction? Well, our profit is going to be equal to 1 million minus the 750,000, which is equal to 250,000. That is how much we're going to profit from this transaction, because we will be receiving 4% when the expectation is at 3%. Now remember, it's still a forward rate, it's still an expectation, right? It's not realized yet. So in this case, the value of the contract to the company is 250,000, just the way we had there, but it's going to be discounted for from time 3.25 to today at the OIS rate. So we go back to our board. We say, well, that 350,000 is supposed to be here, and so to find the value of that today, what we need to do is we need to find the present value of this 250,000 all the way to today. So we're going to be discounting the 250,000, and the rate that we're going to be discounting it using is the OIS rate. And that's how we will be working on this. Okay. The next scenario is the following. Well, suppose that the rates actually prove to be 4.5 with quarterly compounding. So what does that mean? It means that at this point we are not working with I'm going to use a different color here. At this point we are not working with the forward rate anymore. So we are not today, we are 3 years from today. 3 years from today, it turns out that the rate that we can observe for the next year is not going to be the 3% according to our forward calculation when we were here. Now we're here, the rate is not 3%, the rate is 4.5%. So if the rate is 4.5% quarterly compounding, the question is, what is that profit or what is that loss in this case? So what do? Same process as what we had earlier, right? we locked in 4% given our FRA, so we're still expecting to receive 1 million. That has not changed. But then this time we end here. We had year 3. So this is where we are. The market value, or the market rate, is at 4.5% quarterly, which means that we are expecting to receive 1 million based on our FRA, and that was 4% divided by 4 multiplied by 100 million, and that's what gave us the 1 million. And we could have received the 4.5%. So that's going to be 4.5% divided by 4 multiplied by 1 million, by 100 million. And so make sure I get that correct. 4.5 minus divided by 4 equal, and then percentage, multiply by 100, 123, 123. That gets me 1,125,000. So it's going to be 1,125,000. So my FRA locks me in 1 million. I could have received 1,125,000. So the difference again is going to be the 1 million that I'm receiving minus the 1.25 million, 1.125 million. So it's going to be 1.125 million that I could have received, and so I'm essentially going to be losing 125,000 on this transaction. Now this is the 125,000 because the transaction happens in 3.25 years. That's 3 months after the 3rd year, and so we need to find the present value today in 3 years. Remember, this is where we need to find the present value today of that amount. Well, the present value is now we are losing 125,000. So to find the present value, what we need to do is we need to do minus 1. So the present value, I should say PV, is going to be equal to minus 125,000 exponential of that rate, C, for a quarter of a year, and T here is going to be a quarter of a year, so 1/4. Right? The quarter of a year is 3 months. This period here is a period of 3 months. Now the question becomes, what is this value here? What is RC? Well, RC is a continuously compounded rate. Remember, when we're discounting, it should have a minus here. When we're discounting, we're always using continuously compounded rate. The rate that we're given here is a 4% quarterly compounding, because we are still in this 4th year, this year that we have here, because we're still in this year, the rate that applies is the 4.5%, but it's quarterly compounding. So we need to convert that to continuously compounding before we can use it. We remember that our continuously compounding formula. So our continuously compounding formula is the number of compounding period multiplied by the log of 1 plus the quarterly compounding rate divided by the number of compounding period. So in this case, the number of compounding period is 4, and we're going to do a log of 1 plus the quarterly compounding rate, which is 4.5% divided by 4, and that's going to give us our continuously compounding rate. So let's do just that. 4.5% divided by 4 equal, and then we're going to do plus 1 equal, and we're going to take the log of that and we multiply that by 4 equal. So that gives us about 4.475%, so approximately 4.475%, and this is going to be the continuously compounded rate that we're going to be using to discount that value. So the present value is therefore going to be minus 125,000 multiplied by the exponential of minus our continuously compounded rate, which is 4.475%, multiplied by t, and t is going to be 1/4. Remember, t is 3 months, right? And 3 months is if 1/4 year. That's what we're gonna have. And so let's pull a calculator. That is our continuously compounded rate. So we can go back and divide that again by 4. So if we divide that by 4, equal, that gives us that minus sign. We take the exponential of that, so second function exponential, and then we multiply that by 125, 123 equal, so 123,609. So the present value here is going to be equal to minus 123,609. Alright, so our forward rate agreement locked us in a 4%, right? And what we were able to do is, because we're in year 3 already, that's what the 4.5% quarterly rate here is. We are essentially getting 4%, but we could have gotten 4.5%. That's what creates this loss of 125,000. And then we find the present value of that loss. And the present value of that loss uses a continuously compounded rate. Remember that. And so you are going to have to convert the quarterly rate that you have into continuously compounded, so you can use it in order to discount this loss here and find the present value of that contract at that point in time. Now let's summarize this formula for us a little better. So let's go back and squeeze this. I'm going to try to put this all into one page. There we go. So in this case, what did we have? The value that we had here, the 250,000, was equal essentially to the 4% divided by 4. I'm going to try to summarize it here. It's going to be 4% divided by 4 multiplied by 100 million minus the 3% divided by 4 multiplied by the 100 million. And so I could generalize this by saying, well, I'm going to take the 100 million, factor out the 100 million, so it gives me 100 million multiplied by 4% divided by 4 minus the 3% divided by 4. Now there's the 1/4 there that I can also factor out, so that gives me 100 million multiplied by 1/4 multiplied by 4% minus 3%. Okay, so that's what we get there. Now we said we're going to call the 4% RK, and we're going to call the 3%, which is the 4% was RK, and the 3% was our forward rate. So that's going to be RL or RF for our forward rate. And we said we're going to call our principal L. So what we see is that the outcome here of our contract, of the value of our contract so far, is going to be equal to L, which is the principal amount, multiplied by RK minus RF, which is our forward rate, and we're going to multiply that by 1/4. Now, what is the 1/4? The 1/4 is the difference between the 3 years and the 3.25 years. So if T2 is 3.25 years, that is this point here, and T1, it is 3 years, that's that period there. T2 minus T1 is going to be 3.25 minus 3 is going to be 0.25, which is equal to 1/4. So we can simply say that this value here is equal to L RK minus RF multiplied by T2 minus T1. This is the value of the contract at this point in time, but we still need to discount it. So in order to discount it, we're going to apply this, because this value here is going to be exactly the same as what we have here. And so we're going to discount it by applying the following. We're going to say L RK minus RF T2 minus T1, and then we're going to take the present value, which is E, minus the continuously compounded rate multiplied by T2 minus T1. And that T2 minus T1, depending on how far it is that we are, is going to be that difference that we are looking at. So that's what our continuously compounded rate is going to be. If we are discounting for that period of time, this is going to be the annual rate, and so the T2 here is going to match that period. So this is going to be the value of our forward rate agreement. That's how we're going to be valuing our forward rate agreement. All right. Next, what we're going to do is, that's essentially what we have here. The payoff is 125. That's the payoff at 3.25 years. So the FRA is settled in the third year, not in the 3.25 years. So we can find the present value of that cash flow at from 3.25 to 3, and that's what we did here when we computed the present value of the cash flow, which is the outcome here for that period of time, and that's what we obtained here. So what we're going to do finally is talk about the term structure of interest rates, or the term structure for zero rate. And what that is nothing else but the shape of that zero curve that we looked at earlier. And if we go back to this slide here, we remember that we talked about the upward sloping zero curve or the downward sloping curve. And really, that shape is a function of what's happening in the market. And there are three theories that support that behavior, or that are competing to explain why it is that we're observing an upward sloping shape or a downward sloping yield curve. The first one is the expectation theory, and it's fairly straightforward. It says that forward rates are equal to the expected future zero rate or the expected future spot rate. So we expect that increasing curve, right? Because the future value, or in the future values are always higher, quote, than the present value. The market segmentation theory essentially says that short, medium, and long-term rates are independent from each other. And so the idea here is that that curve can be split into three segments. Those are the short, the medium, and the long term. And these are completely independent from each other. And the location of the curve here is a function of demand and supply in this area, the demand and supply in this area, and demand and supply in that area. And so they are preferences, if you will, that investors have for each one of those. And so the curve can be downward sloping, can be upward sloping. They are completely independent from each other. And so that explains that independence here explains the shape of the curve, right? The demand and supply might be higher than it is for the short-term rate, for the medium-term rate, and long-term rate, which explain that upward sloping curve. And the last one is the liquidity preference theory. And the liquidity preference theory essentially says that forward rates are higher than expected future spot rates. And the reason that this works is because the liquidity preference theory says there are two investors and borrowers have preferences that are different. Investors prefer the short term, whereas borrowers prefer the long term, right? So if you're a borrower, you prefer to borrow at the long term rate and you're an investor, you prefer to invest at a short-term rate to maintain liquidity. The simple basic way of looking at it is if you're an investor, you want to be able to minimize the credit risk, and so you want short-term investments because long-term investment come with a longer credit risk. If you're a borrower, you want to delay those payments as much as possible, provided that rates are not so high, in order to maintain liquidity as well. Alright, so that liquidity preference theory, and if we look at this, it is an extrapolation of what the liquidity preference theory essentially says, is that if you're an investor, which means you're a depositor, or if you are a borrower, which is your buyer of a mortgage, right, or you're purchasing a mortgage, we have two maturities, the short term and the long term. And so in this case, the borrower, which is the mortgage here, would be borrowing at the long term, which is the 6% rate, whereas the investor would be investing at the short term, which is the 3% rate. Now, the problem with the bank that's allowing this to happen is essentially the following, is that the bank is going to issue a loan at 6%, right, for a period of 6 years, or a period of 5 years. And however, the bank is going to have deposit of 3% for a period of just 1 year. So if interest rates change, the profits that the bank makes here is the interest that they get on the loan that they make, right? Because you pay the bank, you pay interest to the bank at 6% as the borrower, and the bank turns around and pays the depositor an interest rate of 3%. So this works for the bank, so long as interest rates do not change, right? And so if we have a timeline like this, and that's 1, 2, 3, 4, 5, and 6. The bank is going to be getting 6%, 6%, 6%, 6%, 6%, 6%. That's what the bank is getting. And that's an inflow because the borrower is going to be paying the bank that rate. Now, the depositor, which is the investor, is going to be receiving 3% from the bank, so minus 3%, but that's going to be receiving 3% only for 1 year. Actually, this is for 5 years, not 6 years, so I'm going to remove that last year. So the depositor is going to be receiving 3% for 1 year, which means that the bank is going to have a profit of 3%, which is fine so far, right? Now, the issue is, what if over this second period here, from 1 to 2, interest rates rise? This is not 6%, this is not 3% anymore, it is now 4%. Well, if it is 4%, it's still okay for the bank. The bank pays 4%, makes a profit of 2%. The 6% has not changed because it's a long-term rate, it's locked in. Now, how about the next one? Well, what if interest rate increase for more? Let's say interest rate is 6% now for the next year, because the investor only work 1 year at a time. So if the interest is now, let's say 6%, the bank is going to make 6% here no matter what, because that's locked in. And the bank is now going to pay 6% because interest rate has changed. So the bank is going to make a profit of 0. Let's say for the next year, interest rate is now 8%. If interest rate is 8%, the bank is going to lose 2%. And that is a problem for the bank. So this scenario works for the bank so long as the interest rates do not increase over time. And so the way the bank corrects this mismatch that we see between the assets here and the liabilities is by adjusting the rates in order to provide an incentive to both parties to enter into short or long-term rates. And so that's what the liquidity preference is all about. So to match the maturities of the borrowers and the lender, a bank has to increase long-term rates above the expected future short rates. And that is what the liquidity preference essentially says. It says the forward rate, which is our long-term rate, are going to be higher than our expected future 0 rate. And in that example, the bank may want to be doing just the following. So the bank may want to be, instead of keeping the long-term rate here at 3%, the bank may increase it to 4%. And so what this would do is the depositor or the investor may say, well, I'm getting more return if I'm investing on the 5-year than the 3%. Therefore, I'm going to be investing for 5 years here. And the borrower in this case is going to say, well, I'm paying less for 1 year, so I'm going to be investing for the 1-year period. And so in that case, what's going to happen is this new 1, 2, 3, 4, and 5. So what's going to happen is the bank is going to receive 6% for 1 year. So the bank is going to be receiving 6%, and the bank is going to pay 4% for 5 years. So the bank is going to pay 4% here. And so the bank is going to make a profit of 2%. Now, over the next year, if interest rates increase, the bank is going to charge more. So the bank is going to charge, if the interest rate increases to 7%, the bank is going to charge 7%, but the liability is still at 4%, so the bank is still going to pay 4%, and therefore the bank is going to make a profit of 3%. If interest rate increase even further, the bank is going to charge, let's say interest rate go to 9%, the bank is going to charge 9% and pay 4% and make a profit of 5% for the 5 years horizon. And that's how liquidity preference theory works. It is depending on what the mismatch is and what the preferences are, the interest rates are going to be adjusted for to account for that, to make those corrections. Alright, so this wraps up this unit. I know it is a long unit when we talk about interest rates and we talk about the various kinds of interest rates. We talk about the changes that we need to do from continuously compounded to from quarterly compounded, monthly compounded to continuously compounded rates, and vice versa. And we also talked about the conversion, how to compute the forward rate, how to the bootstrap method, how to recreate our zero curve. And we also talked about, yes, the forward rate. And finally, we talked about forward rate agreements, and we learned how to value forward rate agreements. We said forward rate agreements are going to be valued as the present value of the outcome over that period, right? The period over which the interest is to be received or to be paid. And that is how forward rate agreements are going to be computed and valued, and this is how we said that the valuation of forward rate agreements are going to be estimated. Now, it's a really long unit, so spend some more time working on it and watch the videos over and over if you have to. Alright, I will see you in the next video for the next unit.